So here we've got our torso model, and of course we've removed the pectoral muscles, the integumentary system. We've also removed the ribs, and we know that this region is the thoracic cavity. And the thoracic, thoraco means chest, and the thoracic cavity is going to contain the lungs and the heart. And as you can see, the lungs are going to surround the heart, and by surrounding the heart, it shares that intimacy with the heart, because if the lungs were farther away, oxygenation of the blood and getting rid of carbon dioxide wouldn't take place in a timely manner, and all of our cells needing oxygen and to get rid of carbon dioxide in a very rapid fashion, they have to do this very quickly on a second by second, minute by minute basis. And so you can see that the heart is literally surrounded by the lungs. Each of the lungs is contained within a membrane called the pleural membrane. And the membrane that sits right on the lung itself, the part of the membrane that sits right on the lung itself, would be called the visceral pleura. Viscero means organ, and pleura, of course, is the membrane again that covers each lung. And then the part that would be up against the chest wall, that would be the parietal pleura. Okay, so this membranous sac that encompasses the lungs is going to be double-sided, and it's going to contain a part that's right up against the lungs, the visceral pleura. It's also going to contain a part that is up against the thoracic wall, and we call that the parietal pleura. Now, the heart, since it is right in the middle of these two structures, it has to have a membrane that surrounds it as well. Okay, and the membrane that surrounds the heart is the pericardium. And the part of the pericardium that literally makes direct contact with the heart would be the visceral pericardium. And the part that is up against the chest wall, that would be the parietal pericardium. Now, these membranes contain a lubricating fluid that ultimately keeps them from impinging upon each other. The lungs need to be able to expand when we expand our rib cage, bringing in atmospheric air, and ultimately we can extract the oxygen from the atmospheric air and get that oxygen into the bloodstream. And then when the thoracic cavity gets smaller, pressure outside of the body now is going to be due to the changes of the dimensions of the thoracic cavity, pressure inside the body is going to be higher than outside of the body, so carbon dioxide will flow out because it's going down a pressure gradient. And so ultimately, if we didn't have these membranes surrounding the lungs, they wouldn't be able to expand and contract. They'd stick to the thoracic wall, they'd stick to the heart. The same with the heart. Because it is so closely associated with the lungs, if it weren't contained within the pericardium, then it would stick to the thoracic wall, or it would stick to the lungs. And so it wouldn't be able to contract and push blood out of the right ventricle to the lungs, or push blood out of the left ventricle to all parts of the body. So again, these membranes that surround each of these organs are very important. Okay. Now, we'll start with the heart. And of course, this is just a miniature model. And the heart is about the size of your fist. And the heart is going to fit into a region in the thoracic cavity called the mediastinum. And there went my camera. But the mediastinum is going to be this region that contains the trachea, and you can here you can see the trachea. It's going to contain the trachea as well as the heart, and you can see how the heart fits right into the thoracic cavity. And like I said, this specific area of the thoracic cavity, which is the mediastinum. Now, the heart, this is going to be over here is the right side of the heart. I know it's backward on my camera, but this is going to be the right side of the heart. Okay, this is patient right. And ultimately, the right side of the heart, you will see this structure right here. This is the superior vena cava, and it's kind of tough to see it here, but this is the inferior vena cava that would be leading right up to the heart. And it connects to the right atrium. And the superior and inferior vena cava are going to carry oxygen poor blood full of carbon dioxide to the right atrium of the heart. And the right side of the heart is going to be a receiving chamber for deoxygenated blood from the entire body. And the heart, we're going to find out, is actually two pumps. It's a right side pump and a left side pump, divided by a muscular central region called the septum. And the septum is going to make sure that deoxygenated blood doesn't come into contact with oxygen-rich blood or vice versa. So here we see the superior vena cava and the inferior vena cava. They would both have openings into the right atrium, and then from the right atrium, blood would flow through the tricuspid valve. It's a valve with 3 flaps or cusps into the right ventricle. Okay, the right ventricle is the muscular main pump on the right side of the heart, and it's going to be responsible for pushing blood through the pulmonary semilunar valve to the pulmonary trunk, which divides into the right and left pulmonary arteries. Okay. And so this is going to be your pulmonary trunk that's going to divide into the right and left pulmonary arteries, carrying deoxygenated blood to the heart, to the lungs. And when that blood gets to the lungs, then we're going to see what's called gas exchange occur. If we look over here, we're going to see that in the lungs, gas exchange occurs. The lungs are going to be made up of millions upon millions of tiny alveoli. And so here we have the trachea. The trachea is going to divide into, hopefully everybody can see that. The trachea is going to divide into the right and left bronchus, and the bronchus on each side is going to end up branching into many smaller airways called bronchioles. Those bronchioles are going to end in very small air sacs in clusters like grapes called alveoli. And so when we think of the lungs, we can't think of the lungs as being two big balloons on either side of the heart. We have to think of the lungs as being millions upon millions of tiny individualized air sacs. Now, each one of these air sacs is going to be surrounded by capillaries. As a matter of fact, the alveoli and the capillaries are so thin that they actually share membrane walls. So the alveolar capillaries are basically sharing a wall with the alveoli themselves. And so ultimately that leads to each individual air sac, if this is an alveoli, being completely surrounded by a rich capillary network. And so when the right side of the heart has pumped deoxygenated blood through the right pulmonary artery into the right lung and the left pulmonary artery into the left lung, and those pulmonary arteries break down into smaller arterioles, and then the arterioles break down into arterial capillaries. Well, those arterial capillaries are going to surround the alveoli. Thus, we can get the deoxygenated blood into the alveoli, and that carbon dioxide will move from the alveoli to the bronchioles, up the left bronchus in this example, up the trachea, and then out through the nasal cavity or the oral cavity. So now we get rid of carbon dioxide that way. But when we inhale, we take in atmospheric air and extract oxygen. And so when we extract oxygen, okay, oxygen is in that alveoli, and we have venous capillaries that form a network that those venous capillaries are surrounding the alveoli as well. And so the venous capillaries converge into bigger vessels, venules. Then they converge into still bigger vessels, the pulmonary veins, and we have the left and right pulmonary veins coming from the left lung and the right lung. And the pulmonary veins are going to enter in the heart at the left atria. Now, the left atria is going to have oxygen-rich blood, and that oxygen-rich blood is now going to go from the left atria through the mitral valve. The mitral valve may also be called the left atrioventricular valve because it separates the atria from the ventricles. It might also be called the bicuspid valve because it has two cusps or flaps. And so ultimately, oxygen-rich blood now moves from the left atria into the left ventricle through the mitral valve, and the left ventricle is a much more muscular structure than the right ventricle, and so that additional muscle mass gives the left ventricle enough force to be able to push the oxygen-rich blood out through the aorta, and then the aorta is going to have branches that will carry blood to the brain, the carotid arteries. It also, as you can see, wraps around the back of the heart as well. We call this the descending aorta, and that's going to carry oxygen-rich blood to all the organs below the heart. And so this left ventricle has to pump with enough force so that ultimately all of the miles and miles of arteries that make up our body get this oxygen-rich blood under enough pressure to where it can make its way through the arteries, arterioles, and arterial capillaries that surround each individual cell in our body. And ultimately, that's why the left ventricle has to be so much more muscular and have the ability to contract with more force, because it's going to be pushing the oxygen-rich blood through so many more miles of arteries than the short distance from the right ventricle to the lungs. Okay, because again, remember, the right ventricle only has to pump the blood to right here. Whoops, I'm sorry, blocking my model. Okay. The right ventricle only has to pump the blood to right here, okay, where the lungs are located. Okay. So again, just the proximity of where the lungs are in relationship to the heart, that dictates that the right ventricle doesn't have to be as thick and muscular as the left ventricle. So there we can see the intimacy between the heart and the lungs. The close proximity allows gas exchange to occur, and gas exchange, of course, is going to be essential. Our cells have to have a never-ending supply of oxygen. They also have to be able to pick up. The cells also have to be able to have their carbon dioxide picked up, so they don't build up too much carbon dioxide. Building up too much carbon dioxide leads to carbonic acid formation, and that can make the patient actually become acidotic. Well, the heart is pretty amazing in that it actually has its own electrical system. Okay. And we say that the heart has two types of cells: autorhythmic cells and contractile cells. So the autorhythmic cells are going to be like the heart's own internal wiring, its own internal nervous system. And so these autorhythmic cells are going to stimulate the contractile cells to contract. And the example I like to use is, if you've ever seen Indiana Jones in the Temple of Doom, there is a scene where Indy and Short Round are watching a shaman conduct a ritual, and he reaches inside the guy's chest and he pulls out the guy's heart, and the heart is just sitting there still beating. And so that's not that far-fetched, because the heart, having these autorhythmic cells, gives it the ability to beat on its own. Even if we didn't have nervous innervation of the heart through the sympathetic and parasympathetic nervous systems, the heart could still beat on its own. The parasympathetic and sympathetic branches of the nervous system simply make the heart speed up if the heart needs to speed up because of the fight or flight response, in an effort to produce a higher cardiac output to our working muscles if we have to run or if we have to fight. Or if it's under control of the parasympathetic nervous system, then it slows way down. And so that leads to a lower heart rate during times of inactivity or rest. But these autorhythmic cells will stimulate the contractile cells to contract, and it's that contraction that pumps blood out of the heart. And if it's from the right side, it goes to the lungs. If it's from the left side, it goes to all parts of the body. So the electrical conduction system of the heart is what produces this on the EKG, the electrocardiogram. The P wave, Q, R, S, and T waves. This is going to be what we would refer to as the cardiac cycle. Okay. The P wave equals atrial depolarization. Okay. That's the electrical activity that must precede mechanical contraction. So the P wave is atrial depolarization. Shortly after we see this P wave, we would see the atria start to contract. The QRS equals ventricular depolarization. Okay. So shortly after we see this QRS complex in the cardiac cycle, we would see the ventricles contract. Finally, we see the T wave. The T wave equals the ventricles repolarizing. That means they're resetting and they are now able to take in a period of rest and allow the cycle to start itself over with the right atrium filling with blood and getting ready to have the left atrium fill with blood as well and push deoxygenated blood out and then oxygenated blood out of the left side of the heart. But we refer to this as the cardiac cycle, and it's due to the fact that the electrical conduction system of the heart, carried out by the autorhythmic cells, telling the contractile cells when to contract, allows the heart to work in a rhythmic and efficient fashion to pump blood through as much as 62,000 miles worth of vessels. And that's enough to stretch you on the earth about 2.5 times. Now,
Professor Bernard.
Yeah.
I have a question.
Sure.
So, I have two actually. So, like when we're coding records and speaking about these people that have cardiac arrest. So, if a patient is coming in via EMS, a lot of times the coders will see, okay, the EMS was called to the house because the patient was in respiratory distress, had difficulty breathing. On the way to the hospital, the patient suffered cardiac arrest. And when they reached the hospital, they tried all of the resuscitation methods, and the patient subsequently expired. So a lot of times, the coder might want to code the the cardiac arrest, but unfortunately, we cannot code those under those circumstances because the reason the patient was coming in to the hospital was because of that respiratory distress.
Correct.
So that's one thing I've been seeing that we've been getting tagged on a lot. And the other thing I just wanted to ask you, so like if a person gets electric shock, short of electrocution, this causes that arrhythmic rhythm to just go haywire, and that's what causes that. Can you just explain that a little bit?
Sure. Let me answer the first question first. Respiratory arrest. Respiratory arrest obviously means cessation of breathing. It could start off with trouble breathing. It could be due to pneumonia. It could be due to um, a whole bunch of different issues. For example, inhaling fumes from a fire. If somebody got pulled out of a house fire, for example, their airway passages may be injured, may be damaged due to inhalation of the smoke and the vapors. And so that could lead to respiratory arrest. And of course, if somebody goes into respiratory arrest, then they're not going to have the ability to oxygenate the blood. And so those alveoli are not going to fill with oxygen. They're not going to be able to get oxygen into the bloodstream in a timely manner. And that's going to lead to the red blood cells not having oxygen to pick up, more and more carbon dioxide being created by the cells, carbon dioxide levels building up, and ultimately the patient not being able to oxygenate their tissues. Well, the heart muscle itself has to get oxygen or it won't make it. If we look at my heart model, and I know it's small, but right off of the aorta, you can see branching right off of the aorta are the coronary arteries. The reason that we were designed this way, obviously, is because when the left ventricle contracts and pushes blood out through the aorta, that blood is under the most pressure and it has the highest oxygen content, and so therefore it very quickly gets into the myocardial cells, the contractile cells, and oxygenates them because they have to work 24/7. And so very quickly, highly oxygenated blood under a lot of pressure moves through those coronary arteries and gets to all parts of the myocardium very quickly. Now, if somebody goes into respiratory arrest, if you could imagine how irritated you would be, and I don't just mean irritated, frustrated, I mean how you would be flapping and struggling if somebody, you were getting ready to get up out of a pool and somebody in turn pushed your head underwater, you'd be flapping and struggling to try to get to the surface to get a breath. Well, the heart starts to do the same thing. And so what oftentimes happens is because the heart is getting deprived of oxygen-rich blood, this myocardium is not getting the oxygen-rich blood that it needs from the coronary arteries. That leads to the myocardium becoming very irritated, and that irritated myocardium leads to electrical activity that is not rhythmic and regular. And so what happens is, instead of the normal pacemaker of the heart, I want to draw a very primitive heart here. I'm not much of an artist. But here's our four-chambered heart. Here's the septum, which divides the right side of the heart and the left side. In the right atrium, we have what's called the SA node. Okay, the SA node, the sinoatrial node, is the heart's pacemaker. And what it's going to do is send electrical impulses into the rest of the right atrium and the left atrium. Then electrical impulses are going to move to the AV node. The AV node sits just above the ventricles. It's the atrioventricular node, hence AV. And so the AV node is then going to divide into the bundle, the AV bundle, or it may be called the bundle of His, H-I-S, after the researcher that discovered it. And the bundle of His will divide into the right and left bundle branches, and then those bundle branches divide with a whole bunch of projections called Purkinje fibers. That way the entire myocardium gets innervated with electrical impulses, so the cardiac cycle can occur in a rhythmic and timely, organized manner. Well, when that heart gets deprived of oxygen because the patient went into respiratory arrest, that leads to other areas of the heart being very irritable. Well, anytime you have muscular contraction, whether it be the bicep or whether it be the heart, you're going to have electrical impulses given off. And so if you have other areas of the heart quivering, being jumpy, being irritated because they're not getting the oxygen that they need, that's all going to evoke electrical activity. And we could have various points of electrical activity throughout the myocardium, and instead of getting an organized rhythm that we would normally see on the EKG, we get something that looks like the battle ropes that they're using at the gym to work out with. Okay, something with no organized electrical activity, which is ventricular fibrillation. Instead of the ventricles filling and then contracting and filling and contracting in a rhythmic, coordinated, and timely manner, they just sit there and quiver. They don't take enough time to fully fill, then they don't take enough time to fully contract and push the blood out either. And so that's what leads to cardiac arrest. Ventricular fibrillation is the main culprit when it comes to the heart going into cardiac arrest. But in the case that you mentioned, respiratory arrest occurred first. It deprived the heart muscle itself of oxygen-rich blood. Okay, the alveoli couldn't fill with atmospheric air and extract the oxygen and get it into the bloodstream, and then ultimately get it quickly into the coronary arteries to nourish the myocardium. The myocardium, being deprived of oxygen, got very irritable. When something gets irritable, it acts up. And so all of these little hot spots develop in the myocardium, which leads to a very disorganized rhythm. And so with that lack of organization leads to the heart no longer being able to fill fully and then contract and eject that blood to all parts of the body. And so the brain gets deprived of oxygen. As we already said, the heart gets deprived of oxygen, but all the other vital organs get deprived of oxygen as well. And so you cardiac arrest long enough, you go into multi-organ shutdown. But in the example that you talked about, again, it was respiratory arrest that ultimately led to cardiac arrest. Now, in the case of electrocution, let's say that we have a patient that goes into VFib. And VFib is, again, no real organization. If somebody goes into VFib, the first thing the clinician is going to say is, we need to call a code, we need to get the defibrillator in here or the AED. And what they're going to do when they bring the defibrillator or the AED, they are not going to energize the heart, recharge the battery. What they're going to do is that SA node that was the pacemaker of the heart and set the organized rhythm in motion. What they're going to do when they defibrillate that patient is they are going to take a lightning bolt, discharge it into the myocardium, overload that SA node with so much electrical energy that ultimately, just like the surge protector on your computer clicks off, it's going to click off. And of course, what does your computer do when you get a power surge? It shuts itself down. And so if you look at the EKG immediately after somebody is defibrillated, you would see a flat line. Now, the hope is after they've been defibrillated that the SA node comes back online and then gives us some sort of a rhythm that's organized and can produce a cardiac output. Okay, because this is definitely not producing a cardiac output. The chambers don't have time to fill. The chambers don't push the blood out in a timely manner, in an organized manner. And so ultimately, the goal of defibrillation is to so overload the heart that, or excuse me, so overload the SA node that it shuts down, hence no electrical activity showing up on the EKG, and then it comes back online, leading to a rhythm which can sustain a cardiac output. Now, if somebody gets electrocuted, okay, there's my pacemaker again, my SA node, and let's say our patient gets electrocuted. What ends up happening in terms of the heart is that if they're only electrocuted, like you said, short of so much energy being discharged into them that it kills them, what ends up happening is similar to the myocardium not getting the oxygen that it needs. The electrical activity has kind of acted as a short circuit, and now it makes other areas of the heart irritated. Again, similar to what happened when there was a lack of oxygen for the myocardium. And this lack of organized electrical activity because of all of these short circuits produces some sort of a change in the heart rhythm. And it might end up being that they get something like VFib, or excuse me, AFib, I apologize, atrial fibrillation. Where we have some organized activity of the ventricles, but there is this wavering baseline here in the atrial region because we have other areas besides the SA node fighting to try to take control because of this abnormal amount of electricity that was ultimately responsible for short-circuiting the normal electrical nervous system of the heart, the autorhythmic cells. And so in this particular case, we see a situation where there's disorganized atrial activity, and that leads to less than optimal cardiac output because the atria don't push as much blood into the ventricles as they normally would, and that leads to ventricles that don't fill fully, and that causes a less than normal cardiac output. You lose what's called the atrial kick. The atria supply about 15% of the total cardiac output. And without that 15%, the person doesn't have the normal stamina, the normal endurance that they would have. Activities of daily living would have a tendency to fatigue them. And probably the only way to correct this situation would be to perform a technique such as an ablation, where they would go in through a catheter, either in the groin, or now they do a lot of those through the forearm as well. But the ablation is going to be a technique where they will try to pinpoint exactly these irritable areas, and they will use electric current to burn them out and find all of the little areas where we have what are called re-entry points of electrical activity, and they will literally burn those and make scar tissue appear there, and scar tissue doesn't conduct electrical activity. So that leads to what they hope is the SA node being in control and producing the normal cardiac cycle that we're used to seeing on the EKG versus something that's disorganized like we see in the example above. Okay. So that's what can happen if somebody gets electrocuted. Again, short of being basically causing cardiac arrest, which it very well can do. It can overload the heart to the point where the heart never recovers. But again, in this other example, it just led to an arrhythmia or dysrhythmia, and that dysrhythmia led to a less than optimal cardiac output. Okay. Did that answer your question?
That was a really good explanation. And
Sure.
I was often wondering sometimes before I got to understand about that. I see people reading those cardiac scripts and they act like they know what they read.
Right. Well, in some cases, if that person was electrocuted, they might also have to have a pacemaker implanted. The pacemaker, of course, is going to be an artificial version of the SA node. And that artificial version of the SA node could be set to basically beat however many times a minute the patient needed to sustain an effective cardiac output. And that would allow a better electrical conduction to occur. And it could be programmed. Yeah, it could be programmed to however much cardiac output they needed. For example, pacemakers in this day and age are so advanced that they are called demand pacemakers. If, for example, I have the need to go up some stairs and my heart rate needs to go up to 100 beats a minute, the pacemaker can cause my heart to beat 100 beats a minute. Whereas in the past, pacemakers were set at a certain heart rate, and if you needed to go up to 100 beats a minute to go up a couple flights of stairs, it just wouldn't happen. It was set at 80 beats. That's all you got. And you'd get the first flight of stairs under your belt okay. You'd get a few steps into that second flight, and you would be done. You'd have to stop and rest till your heart rate came down, or you'd get so fatigued and short of breath that you would stop anyway. You just couldn't go. So in the case of somebody who was electrocuted, if they couldn't correct it with an ablation, they might actually have to go in there and install a pacemaker to make sure that they had a cardiac rhythm that would supply a decent cardiac output.
That's a good explanation, and I like your explanation on the respiratory event, because now by how you explain it, you can actually visualize it.
Mm-hmm.
If you're coding, you can actually visualize. Okay, I can't use cardiac arrest because
that was secondary, right? Mm-hmm.
I mean, that it happened, but that's not what the patient healed.
Right, right.
That was subsequent results. The heart failure, whatever, the respiratory arrest or shortness of breath is what caused the patient to come in. Because they had cardiac arrest, that would not be a principal diagnosis.
Right,
because
right.
it occurred after. And then again, in some instances, it could be either or. You can have either or.
Sure.
Principal two diagnoses that equally meet the definition of a principal diagnosis, and then you would select that. But of course, you have to go by the coding guidelines. And so I just, as we go through, I just will ask you to give us some examples, because these are the areas in our audits that we have gotten tagged on. So thank you for that explanation.
Well, one thing that I want to definitely point out are children will almost always respiratory arrest, and that leads to cardiac arrest, just like the scenario that we gave. If you have a child that gets an airway obstruction, because obviously kids put everything in their mouth, and if they get an airway obstruction and that airway obstruction isn't resolved, that leads to a respiratory arrest situation, which again if it's not resolved, leads to cardiac arrest. And so in that situation, as soon as you can resolve the respiratory arrest, boom, you probably resolve the cardiac arrest as well. But again, it was the respiratory arrest that led to cardiac arrest. Okay. Does anybody else have any questions about anything? Okay, good. How's everybody doing? Are we feeling pretty good tonight, or I know Dr. Miller's not exactly feeling good, and then I know yeah, I know everybody's been a little bit under the weather. Terry said she had a real brutal cough. Well, that's all I really was hoping to cover from the cardiorespiratory standpoint. I definitely wanted to talk about the anatomy and the physiology of the heart and of the lungs, how they were so intimately linked together because of their proximity, but also because of the need for one and the other. The heart has to pump that oxygen-rich blood, and the only way that it can get that oxygen into the bloodstream is if the lungs are not impaired. And so if we get a disease like emphysema breaks down the alveolar walls, and instead of having millions and millions of tiny little alveoli, tiny little air sacs, we have bigger and bigger just bulbs of these alveoli. And what that ends up doing is decreasing surface area, and decreased surface area means it's slower to get oxygen from the alveoli into the bloodstream. And of course, the other thing about emphysema too is when those tiny alveoli have the alveolar walls broken down, okay, and we said the alveolar wall is so thin that it actually shares its wall with the alveolar capillaries. Well, surface area decreases, gas exchange decreases, and those areas where the alveoli are broken down, we actually have trapped air there. And so that trapped air leads to less movement of atmospheric air into the alveoli, less movement of carbon dioxide out of the alveoli. And so we end up having deoxygenated blood that builds up, so oxygenation levels are low. We see cyanosis appear. We see peripheral cyanosis in the nasal membranes, around the lips, and even in severe cases, they can be blue from head to toe. When I was in cardiopulmonary rehabilitation, we would have patients with severe emphysema that if they didn't wear their oxygen into cardiopulmonary rehab, they would be as blue from top to bottom as a Smurf. I mean, the other patients would be just scared to death something bad was going to happen, and I'd be like, oh no, Mr. So-and-so just didn't wear his oxygen in from the parking lot. He'll pink up as soon as we give him some oxygen. And sure enough, they would. But what ends up happening again is when you have that trapped air, when you don't have a way of getting rid of your carbon dioxide or in picking up oxygen and getting it to the tissues, you do become cyanotic. You do start to see the tissues not getting oxygenated, and then the body has to start deciding, okay, we have a limited amount of oxygen. What do we need to do to maintain our survival? Well, we need oxygen going to the brain. We need oxygen going to the heart. Okay? Things like the tissue, I'm sorry, but you're going to be blue and you're going to start to break down. You'd start to see it on those severe COPDers around their elbows and stuff because they just weren't getting the nutrients and the oxygen to the integumentary system, and that led to those membranes breaking down. And so, again, we see this intimacy between the heart and the lungs. The two systems must have each other. And that's why, again, a lot of textbooks call it the cardiorespiratory system. And again, that's why in ICD-10, they are meshed together into the cardiorespiratory system. Okay. Any other questions about any diseases related to the heart or to the lungs or the structures associated with the heart and the lungs? Okay. Well, we covered 3 chapters that I'd hoped to get through tonight. I made sure, everybody earlier in the week got the videos for these, so hopefully everybody had a chance to look at the videos and come into class all ready to go. But let's just plan on going ahead and wrapping up here. And next week, we'll start with the digestive system, and then we'll get into the integumentary and the urinary system. And since the urinary system is linked so intimately with the male reproductive system, we'll probably be able to cover it as well. Okay? And I sent out some more videos getting through all of those. I'd sent out the digestive system some time ago, but I got through the urinary system and even into the musculoskeletal system earlier today. So everybody should have the videos that they need to get schooled up before next week. So unless anybody has any questions, we'll go ahead and plan on wrapping up for the night. Everybody good? All right then. Well, if anybody has any questions, you guys know where to get a hold of me, okay?
Thank you very much.
All right, ladies, I hope you all get to feeling better. Sorry that everybody was sick at the same time.